And we welcome also the next one, which is Padgett from University of Glasgow, and the title of his presentation will be Resolution Limits of Quantum Ghost Imaging.
No. Yes, no, okay, super. Well, thank you very much for the invitation to Singapore. Normally when I come here, I say how much better the weather is than it is in Scotland, but I'm not actually sure that's been true these past few days. So it's made me feel at home, all this rain, although the temperature of the rain was a little bit higher than normally. So this talk's going to be a little bit different to many of the other talks that you've heard, in that it's largely experimentally based, and that I'm going to argue ultimately isn't quantum. So let's see how we get on. I'm going to introduce the concept of ghost imaging. That's been around for 20 odd years now, clearly invented long before my time. And I'm going to talk about, in this work, what sets the resolution of a ghost imaging system. How do I understand that? And actually, I'm going to relate that, as other people have also done in the past, to some thoughts that Popper had on the validity of the Copenhagen interpretation of quantum mechanics. So I thought I'd show you a little picture of Glasgow University. It looks a bit like Hogwarts, I know, but it isn't. Actually, our most famous old boy, so to speak, was Lord Kelvin, here of temperature. And at that time, believe it or not, every professor in the university got a rather nice house associated with the university to live in. Sadly, that's no longer the case, but it is my office. So I have an office in what was Kelvin's house, and it still gives me a thrill to see his clock in the morning and his desk and think that he sat there and looked at the time. So we'll see. I'll explain where the ghost come. I'll explain where the ghost comes from shortly. So I've just put some papers up there. If anyone wants a copy of my talk afterwards, you can have it. I've got some memory sticks, and here's essentially the prior art in ghost imaging. And I would say ghost imaging. The first paper which I recognise as being ghost imaging or quantum ghost imaging is by Yanhua Shi and co-workers. And you can even see there in the titles, da 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 da, by quantum entanglement, etc. So certainly, when ghost imaging was first reported, it was at least implicit in the papers that it was a quantum phenomena. And I think that's why it's ghost imaging, because quantum is spooky, and hence why it's called ghost imaging. So here are my co-workers in this present piece of work. Particularly notice Bob Boyd, University of Ottawa and Rochester, who I've now worked with for many years. So this is a nice cartoon. These are not real photons, they're cartoon photons. It's a parametric down conversion, you know. So we have an ultraviolet photon coming in this case into a crystal of BBO, and you generate signal and idler photons at 710 nanometers, and they come out. I've shown them coming out in slightly different directions. Let's just leave that for now. But now what I'm going to do is take a closer look at what's going on in the down conversion crystal. So we magnify. If I looked very carefully at the crystal with some kind of imaging system, I would see a flash of infrared light. The photon has been created, and I don't know where it is. It's going to be somewhere in the crystal, set by the extent of the pump beam. So the diameter of the ultraviolet light coming in here sets the sort of active diameter of the crystal, and somewhere in that diameter I would see not one photon born, but two. Those two photons would be born in what looks to be exactly the same position. So just like Noah's Ark in reverse, the photons come out 2 by 2, and they come out in exactly the same position. So there's a strong position correlation between the down-converted photons, photon by photon. That's completely different to a beam splitter, of course, where a photon comes in and it goes one way or the other. This is a photon pair source, and it's that correlation that we're going to use to make an imaging system. So the basic idea is that you stick the object in one of the beams, and you put a camera in the other beam, and you let go. So it is interesting to note that the photons hitting the camera have never interacted with the object, but their correlated partner has. And that's the essence of a ghost imaging system. Let's look at it now a little bit more diagrammatically. We have a pump photon coming in. My photon pair is born. We have one photon going off to the object. I do not know where it is. The only thing I know is whether the photon is transmitted through the object or not, and that is identified by this thing that's traditionally called a bucket detector, meaning it's big, it has no pixels. The only thing it knows is transmission, yes or no. If the photon is transmitted, this imaging detector measures the position of the correlated pair, because it is essentially going to, all the photons hit here, but I'm only interested in the photons whose partner was transmitted through the object. Now, traditionally, that imaging detector was a scanning photodiode, or scanning avalanche photodiode, or scanning photomultiplier tube. And then you can see, as I showed there, it builds up the image line by line. But that is inherently inefficient because most of the time the detector is going to be in the wrong place to measure the photon, and therefore the maximum efficiency I can ever have is 1 over the number of scan positions, or 1 over the number of pixels in the object. And so it's incredibly inefficient, and it takes time. So why use a scanning detector when you could, as I originally implied, do it instead with a camera? Well, it wasn't done that way originally because cameras could not see single photons. They could see single photons, you have a high quantum efficiency, but they also see a heck of a lot of noise, and so you can't tell the difference between the photon and the noise. That is no longer the case. If you buy a time-gated image intensifier camera from Andor or similar, and as long as you only switch it on for a nanosecond or so, if you happen to switch it on at the right time, then you will see a single photon. You can see a single photon with an intensified camera, and it will be one flash of light against a dark background. Now, how do I know when to switch the camera on? I know when to switch the camera on because I'll switch the camera on only and if this bucket detector records a photon. So here, photon is transmitted. I say, come on, camera, quickly take a picture of the correlated pair and find out where the correlated photon is. Clearly, I have to do that inside the light cone and all that kind of stuff, but we don't really mind about that. Slight problem is I have to let, of course, the electrical signal overtake the optical signal. Otherwise, by the time I've told the camera to do something, it's gone. And so I build into the system a delay line. And so this path here, the electrical connection between this bucket detector and the camera, is a lot shorter than the delay line. And I fix it all up. And hey presto, it sort of works. There's a picture of the experiment. And there is a picture of a transparency of a ghost, a skull, because it's ghost imaging. What else would you image? And so that transparency is placed into one of the arms, and then the other arm records photon by photon. What you're seeing here, of course, is the sum over many, many photons, about 7,000 or so photons. We'll see the image build up in a second. And what you're seeing across the bottom here is what happens as you change the length of the BNC cable between the camera and the detector, i.e. you've got to have the length of this BNC cable exactly right so that when the electrical signal gets here and the camera goes click, that happens at exactly the same time that the photon gets there so it can be recorded. And that's just going to show that if I actually trigger the camera at the wrong time, there's nothing to see. And that just shows you how good the noise performance is of the system. And so here, I hope this is a video that's not going to play. Oh dear. Let's, oh, please, please, please. Ah, good, 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 good. So these are the photons arriving one by one on the camera. clearly what this graphic is doing is essentially summing those, because each flash is essentially one trigger of the intensifier. The intensifier will trigger up to 200,000 times a second, and so in a few seconds you can build up an image of the transparency, bearing in mind that none of those photons have ever interacted with the object at all, but their correlated partner has. Now, just as a little aside, here we see an image with 65 photons in it. It doesn't look much like anything. 600, 6,000, and 70,000. How many photons do I need to form an image? This is a little digression. And just to say that actually you can do remarkably well with a very small number of photons. Why is that? Because images aren't a collection of random things. They show strong pixel-to-pixel correlation. So just like when you save your holiday snaps with a JPEG compression, you can save them in a sort of a tenth of the memory that you might have thought you were going to need because essentially the image is sparse in the discrete cosine transform space. The same thing is true here. And so one can apply essentially all the kind of image regularization techniques that image processors know and love to recover remarkably convincing images from comparatively small numbers of photons. I won't bother to explain how it's done, but effectively I go from here. Now the noise in this image is not really noise. Well, it is noise, but it's the inherent shot noise variation. I get 10 photons in one pixel. The next pixel was meant to be the same intensity, but it's 10 plus or minus root 10, and so on and so forth. And so I go from here, and you see the program actually working. You see this is actually a movie of going from here to here. Some examples there. 7,000 photons becomes this image. 700 photons becomes that image. And so we can recover images. Here I have a wasp wing. No animals were harmed in the making of this paper. I found it dead on the floor. It was able to donate its body to physics, and I used its wing in the microscope. So there we have a wasp wing, and I think that was something of the order of 20,000 photons used to record that image of the wasp. Right, so let's get back. Okay, it's spooky, it's odd, it's interesting, maybe. Is it quantum? Well, I don't have to tell any of you that just because I have position correlation, it's not a uniquely quantum phenomena. What makes it a quantum phenomena is if I have position correlation and momentum correlation, and strictly speaking, that I can make my mind up what I'm going to measure after the photons have left the source. Well, the latter's not true in this case because, of course, everything's with fixed lenses and things. But it is possible to go from this situation where, as I've described, the crystal, the nonlinear crystal, is imaged onto the object. Notice this bucket detector can be anywhere here. I don't care. All it has to do is measure whether light comes through or not. When people talk about seeing through turbulence with a ghost imaging system, they mean if the turbulence happens to be in this bit of the optical path here, because it doesn't matter. All I have to do is measure transmission. It's position correlated. The photons here are position correlated with the photons here, and therefore the image that I'll ultimately recover on this camera is an upright image. If I move now into the far field, then my momentum anti-correlation becomes, in the far field, a position anti-correlation, and the image therefore becomes an inverted image. And so image plane, far field. The image inverts. Is that what we see? That is what we see. And that is sort of a manifestation of an EPR effect, entanglement, whatever you want to say. Clearly, it's not proof thereof because of all the reasons I've said about timing, etc. But essentially, I'm relying on the EPR-like correlations in the down conversion source to either give me upright or inverted images. But quite frankly, if all I was interested in doing was imaging, then either would be sufficient. I don't need to do both. So that's the extent to which it is quantum or not. Right, how can it do something a little bit different? Let's think about how it can be different. So here's the same thing again, the ultraviolet photon coming in, But now my down-converted photons are not both at 710. One of them's at 460, and the other one's at 1.5 microns. But they still share the same position correlation. And so now I can do this. I set up the same system again, the same delay line, but here my object is being probed by the infrared light at 1.5 microns, but my image data is being recorded in the visible at 460 nanometers. And that's rather handy because my time-gated image intensified camera doesn't work at 1.5 microns. The photocathode in the infrared would just be so noisy you'd never do single photon counting. In actual fact, this works better than the other one because 460 nanometers is brilliant for the camera. It's exactly the wavelength of photons that it wants to detect. And so here we go. And then what I've got here is actually a silicon wafer. Normally, light doesn't travel through silicon. It looks like a piece of metal. But if the optical wavelength is 1.5 microns, it does. And so at 1.5 microns, my silicon wafer is transparent. Onto the surface of the silicon wafer is a gold deposited layer, which has got a lambda etched into it. And then here we see essentially an image taken through the silicon wafer of the gold lambda. It was probed by the infrared light, but the image was recorded in the blue. And again, we're still talking about remarkably low photon numbers. Here are the images which you can just about make out. And here are the image processed images, which are again assuming the sparsity condition that I actually mentioned already. Almost useful, maybe. How can it be understood? So that's where we were. That's our position correlated. That's what we do. And clearly, if I was very clever, I could write down lots of two-photon wave functions and things and work out correlations and all of that. But as was pointed out in the early days of ghost imaging, it's really easy to understand. It was pointed out by Klitschko, one of Xi's co-workers, and he said this bucket detector up here, let's replace it with a light bulb. And let's illuminate the object. And so the light now goes back towards the source. And let's replace this crystal with a mirror. And the light bounces off the mirror and then goes off to the camera. So watch carefully. I'll switch between the quantum system and the classical system. Okay? So I've replaced the bucket detector with a light source, and I've replaced the nonlinear crystal with a mirror. And I would expect that the two images I get are effectively the same. And so, in a sense, I'm going to argue, we're talking about classical simulation of quantum systems yesterday, weren't we? I just added this slide. That this is a classical simulator of that quantum system. Yeah, I'm difficult to see that it isn't. Now, you can also do the same thing, of course, by changing the lenses around to get to the inverted image. So there we have the upright image. We now put the mirror into the Fourier plane, and we have essentially an inverted image. I can do all the same things again. And here we have some results which we actually did that literally. And actually in this case, we were using the crystal, the surface. We didn't even bother to replace the crystal. We used the front facet of the crystal as, guess what, a mirror. Taking care for it not to be anti-reflection coated. That was our first mistake. God, we're not getting any light back off this. But anyway, and then our fiber coupled detector, unscrew the detector and screw in an LED. And so we didn't have to, the only thing we actually had to do to flip from one to the other was unscrew the FC connector on the fiber and screw in an LED. And one can see one gets essentially identical images, both in the position correlation and the momentum correlation thing. So there we go. How about ghost diffraction? If I can do ghost imaging, so clearly I can do ghost diffraction, or maybe I can. Here's essentially the classical simulator setup. Here's the object, double slits, no diffraction pattern. Why was that? Because if I illuminate double slits with a light bulb, I get appalling fringe contrast. If I want to do a classical diffraction experiment, of course, I need to put a little pinhole into the system. And then, if I put a pinhole in front of my light bulb and illuminate my double slits, lo and behold, I can get a diffraction pattern. Now, what's the equivalent of that in the quantum system? Well, That's the equivalent of my light bulb. I need to put a pinhole in there if I want to get a ghost diffraction pattern. Oh, make the bucket smaller. So that's it's amazing what you can do in Photoshop, eh? So that's my big bucket. That gives me a horrible blurred mess. That's my small bucket, and that gives me a ghost diffraction pattern. And again, we can read about that. So we're getting closer. Oh, and here's this should be a ghost. This should be double slit diffraction, photon by photon. So we'll see. We'll let some photons arrive, and once you have enough photons there, then you begin to see the interference fringes associated with the double slits. Clearly, there's still there was some problems with some noise in the background on that shot. You see the fringes coming? Okay, there we go. Those are the interference maxima from the double slits. In that case, it was 40,000 photons in the experiment. Real data, not a computer simulation. Now, the title of the talk was the resolution of ghost imaging systems, so I better talk about the resolution of ghost imaging systems. What sets the resolution? Well, first of all, if you've got crappy lenses, that's going to mess up the resolution. There is nothing in this that will overcome the diffraction limit of the optical system. So let's park the diffraction limit for a moment and assume that my imaging system is perfect. What sets the resolution of the system? So that's where we are. Well, one thing that sets the resolution of the system is the aperture of that mirror. That mirror is in the Fourier plane of the object, and therefore, if I make it really small, it's like having a spatial filter in my imaging system. All the high frequency information is effectively at the edge here, and the DC information is in the middle. So if I begin to shrink my mirror, I would expect to see the resolution of that inverted image degrade. Now, what sets the size of the mirror in the down conversion system? Well, I already said that the photons or the mirror size is effectively set by the size of the pump beam. It is the size of the pump beam which governs the extent to which those two photons are correlated in the far field. And the expression is this here. You see that the correlation here depends upon the size of the pump beam, the waist of the pump beam. And it's effectively the same formula. This is the focal length of the lenses that you would have for the size of the pinhole as a spatial filter. So let's set it up a little bit differently. Why have I done it this way? So I did have my object up here, but I want to give myself the option of putting the object and the camera not in different arms, but in the same arm. So I've introduced an intermediate image plane here. These two lenses are extra. And I can do an imaging system either as a ghost imaging system with my object there, or what I'm going to call a heralded imaging system with my object here. What do I mean by heralded? Well, at one level, it's just a normal imaging system. I've got some light generated over here. I illuminate my object. I get my image. Why is it heralded? Because the photons are coming one by one. I don't know when they're coming, but this detector does. So this detector is still used to trigger the camera, and that allows me to build up an image based on single photons. And I want to do that in both configurations. So that's where I am. Let's just flip around. That is essentially the ghost imaging system. That is the heralded imaging system. Superficially, I expect them to be the same. However, notice, in this configuration, the spatial filter is just acting on the light source, and my resolution is simply determined by the quality of my lens system here. In that, oops, panic. In this configuration, the spatial filter is between the object and the camera. And so if I bring in the spatial filter, I expect to see the resolution of this image degrade. And that's going to be governed by the size of the pump beam. So that's the large pump beam. The ghost image and the heralded image are the same. I now make the pump beam smaller. That's fine still. Switch to the ghost configuration, and the image becomes blurred. That's what I expect to see. I expect to be able to control the resolution of the ghost imaging system by changing the size of the pump beam. And I'm now going to go back to double slits. This is my object. It's not the skull any longer. This is the heralded configuration with the large pump beam, the medium-sized pump beam, and the small pump beam. And we see that effectively the resolution doesn't change. The image gets darker because I'm cutting out light. But in that configuration, I mean, this thing here, changing the size of the pump beam doesn't affect the quality of this imaging system. However, in the ghost configuration, as I reduce the size of the pump beam, we see the slits get a little bit blurry, and then they get totally, completely washed out. So clearly, I am degrading the resolution of my image by reducing the size of the pump beam. Let's think about moving forward now to the diffraction case. I've just reshuffled my lenses here. I can have heralded diffraction, or I can have ghost diffraction. In the case of the big pump beam, I might expect that the two things would be the same. But in the case of the small pump beam, that's no longer going to be the case because I've degraded the resolution of the system. It's like making the edges of these slits a bit soft. And when I have soft-sided slits, I lose high-order diffraction orders. That's one way of thinking about it. And so as I go from, this is with the restricted pump beam, when I go from the ghost configuration with very few diffraction orders to the heralded configuration, I get more diffraction orders. That's what I'm expecting to see. And indeed, that is what I see. In the heralded diffraction, my diffraction pattern remains robustly the same, irrespective of the size of the pump beam. In the ghost system, that's not the case. Reducing the size of the pump beam eliminates diffraction orders from the diffraction pattern. So now let's relate it to Mr. Popper. Like all good scientists, I went to Wikipedia to see what he had to say about himself, and therefore clearly it's absolutely correct and accurate. I think it's right. So this was his basic notion. So now he's unwrapped it. I've got my two, rather than I had my photons in a V, he's got his photons going in opposite direction. And clearly, if I put a slit in here, I can cause these photons to diffract. And clearly, if I put a slit in here, I cause these photons to diffract. No argument about that. In essence, his question was this: what happens if I just put a slit at one end? Well, the slit forms a ghost image of the slit here, and therefore surely these photons should still diffract. Essentially, his notion was that I would put the diffraction grating in one arm, and I would cause diffractive spreading in the other arm. That's the thing. And he goes, well, this is a bit strange, because if that's true, that's sort of indicating action at a distance, because I sort of go, drop the thing in here, and all of a sudden I get diffraction over there. And if it's not true, then my whole notion of ghost imaging must be wrong. Now, it was a sound logic, and incidentally, it doesn't cause diffraction for the reasons I've just described. Actually, what this beam does here is set by the spatial correlation of the source. Let me try and explain it a bit better. There's different equivalent ways of understanding it, okay? This is what we had set up. This is my ghost diffraction pattern. And one can imagine if I illuminated it and everything would be fine, I would get some wonderful diffraction pattern over here. And I place the slits in and out, and I get a diffraction pattern or not. However, note also that this plane here is actually an image plane of the crystal. In the absence of doing anything, all I do here is take an image of the source. If there's no slits up here, the photons here essentially map out exactly the spatial extent of the pump beam. Now, when I start doing coincidence counting, I can never see more photons than I was going to see. These are still the photons that I had. What the coincidence count does is it makes a subselection of those photons and reports that as the coincidence image. You know, the coincidence count cannot be bigger than the individual count rates. And so we go back to here. Effectively, what's happening is this is my down conversion source. I've got some natural spreading of the beams. And incidentally, the spreading of the beams is a manifestation of the extent of their spatial correlation. If the spatial correlation is very, very high, the beams spread a lot. If the spatial correlation is low, the beams don't spread very much. I've got a detector here, and I've got an imaging detector over here, and it measures some spatial extent. And let's call this spatial extent here the size of the pump beam. I'm imaging the source. And then, that's my singles. I'm now going to take a coincidence count of those photons with what I detect over here. And the best I can hope for is that I will observe some kind of diffraction pattern or some kind of image, but it cannot ever extend beyond the divergence that was inherent in the beam. So that limitation is effectively what undoes that thought experiment. Putting the slits in putting the slits in over here do not cause additional diffraction over there. They simply pattern the photons that you saw. I can see I haven't explained that very well. Think about it a little, and there we go. So, this is pretty much the conclusion. So ghost imaging is not the same as heralded imaging. I hope I've managed to convince you of that. That the ghost imaging depends on the size of the pump beam, the heralded imaging does not. And that means that if I use a small pump beam, the resolution of the ghost system could be worse than the diffraction limit as set by the lenses. That ghost imaging can be better, it can't be better, than the strength of the correlations dictated by the down conversion source. We've already talked about what sets the spatial correlation in the far field, and that effectively is the momentum uncertainty in the pump. If the pump was infinitely wide plane wave, all the momentum would be going in that direction, and my signal and idler photons would be perfectly anti-correlated. But my pump has finite extent. That means it has a finite uncertainty in its own transverse momentum, and so the down-converted photons have also picked up that uncertainty. So this expression here is effectively a statement about the transverse momentum spread in the pump beam. In the image plane, the formula for the correlation is different. It looks a little bit more complicated. This is the length of the nonlinear crystal. And if you've ever played with parametric down conversion, you'll know if I come in with a light beam, a laser, and I put my crystal in front, and I get down converted light on the wall, it's spatially incoherent. The beam on the wall is bigger than the pump because it's spread out. As I make the crystal thinner and thinner, the light from the down conversion crystal spreads out more and more, and indeed the correlation becomes better. And essentially the diffraction, the spread angle is effectively, sine theta equals lambda over d, where d is the correlation length of the two photons. And so these two equations here represent a limiting resolution for a ghost imaging system. So that's that. If anyone wants a copy of my PowerPoint slides, I have them. You can have them. If you want to read any of my papers or anything, I'm one of those naughty people that loads them all onto ResearchGate so people can download and read them. I hope there's no journal editing. Okay, they're my papers. I think I have a moral. It's okay, but we can argue about that later. So thank you very much indeed.
Thank you very much. Open for questions. We have time. Yes, please.
Hi, thank you very much for your talk. I find it fascinating. I actually want to go back to that slide, the one with Popper in it.
Right.
The equal scatter, because I'm...
Keep going?
Keep going. Yeah, this one. I guess I'm trying to understand here, like, are you saying, probably I'm not understanding this well, is like, if the Copenhagen interpretation is correct, then ghost imaging could therefore happen. And this equal scatter that you're talking about here itself needs to happen for ghost imaging to take place.
So let me be clear, first of all, in that I'm not claiming that I've just shed some humongous great light on the Copenhagen interpretation, nor have I proved the Copenhagen interpretation. I'm just saying the Popper experiment doesn't disprove it. And I think that's recognized. What I was trying to do was explain why, and this is not a criticism, I mean, I think it's a phenomenally insightful suggestion that Popper made, but he made assumptions about how the experiment performed. And so his assumption was that if he put a narrow slit in this arm, he would then observe that the photons in the other arm became more divergent. And it was that additional divergence that he said correctly, either the Copenhagen interpretation is wrong or there's action at a distance. Unfortunately, the argument he made unravels because when you put the slit in this arm, the light in that arm doesn't do anything differently than what it was going to do before. Nothing changes. And so the premise on which his Gedanken experiment was based turns out, with the benefit of 20/20 hindsight, not to be true. And so what I was trying to do here was explain, essentially using the classical quantum simulator, what was going on, and hence explain to us why his original premise on the experiment was wrong. That's, yeah.
Well, I have the microphones. I'll steal the question first. Up here.
Oh.
Up the other way. Up here. Yes. Hi. So did I understand correctly, the imaging process here is that basically when you get a click in the bucket detector, that's the only time when you open the camera or take an image. Yeah. So if the photon is absorbed by the thing you're imaging, then you don't take a picture, and that's why you get a black spot. Yeah. Right. So you're essentially imaging a stencil of a. Yeah. Like
and now you could do the same thing in reflection or scatter or whatever, but yes. And so I recognize that everything I'm doing here is inside the light cone, and therefore in terms of that particular loophole of Bell and EPR type experiments, clearly blown completely.
Okay, yes. And so then you talked about the resolution limit in the end. Is there something that you have to consider when you're using different wavelengths?
Well, that's a really good question. I mean, I would love to be able to tell you that the exciting thing about using infrared light to probe the object, and I'll get there, yeah. I would love to be able to tell you that when you do this, you probe the object with infrared, but you get the diffraction limit of the blue. And you go, wow, I've just improved the resolution of the system by 3. It turns out that that's not the case. If you probe the object with the infrared light, even though you are imaging it in the blue, you get the resolution of the infrared. Yeah. Now, people have published papers to the contrary. I think they're wrong. I wish it were true. I mean, believe me.
That would be cool.
That would be cool, yeah.
So you have a monochromatic entanglement source.
10 nanometers.
Yeah. But can you see any benefit if you would really have a broadband entanglement source?
Well, one thing that you can see that one can do to some extent is you can do depth sectioning. And the limit to which I can do depth sectioning is the correlation length of the photons, which is the inverse bandwidth. So with a 10 nanometer source, the correlation length at this wavelength is about 60 wavelengths. And so I cannot do depth sectioning. If I do a Honger-Mandel dip type experiment, the width of the dip is 60 wavelengths. If I have a broadband source, the width of the dip comes right down. And actually, the classical simulator for that is optical coherence tomography. And so there's an interesting question there. Does doing OCT embodied as a Honger-Mandel dip type experiment, does that have any performance advantage over classical OCT? I don't think so, but I think I'm more on the fence over that than I am over the resolution question of infrared versus blue.
I just remember that there was a paper by Asher Perez many years ago. Many, I mean maybe last century actually, maybe 97 or something like that. Just discussing exactly this question.
Yes, I didn't put that reference up. I put the reference up by Shi. I put two references up by Shi and Loudon, which, as you say, date back to the previous century. Now,
He was a theorist, of course. He didn't
yes.
do the experiment.
Now, I'll tell you why my experiment's better. When you put a single slit, you get a splodge. And it's actually really difficult at low signal to noise to measure the width or the scale or what else has changed. If you do the experiment with double slits, then you get fringes. And effectively, all I have to do is count the number of fringes. I go, number of fringes has gone down. And so it's essentially the spacing of the slits gives you some kind of scale in your ghost image. And so both Popper's original Gedanken experiment and the subsequent discussions, I think, and certainly the subsequent discussions of which I know, all deal with this problem based on a double slit. And you end up comparing widths of top hats to Gaussians and go, oh, I don't quite know how to do that. By using the double slit, it essentially, I think, gives a much cleaner experimental result in that I basically just have to count the diffraction orders. And I go, over here I had 5, then I had 3, then I had 1. And so that, I mean, it's a subtlety from an experimental point of view, but it's actually really, really, really difficult to control the experiment well enough that you can really talk about the divergence of the data. And so that is it. Although, I agree, there was the paper you referred to, I think was published at the same time-ish as the Loudon, as this paper here. I might be wrong there. I think super guy, Rodney, actually. I don't know how many people know him.
Other questions?
Will you be able to improve the resolution with orbital momentum?
Well, my pet topic, orbital angular momentum. I have some slides on that. So funnily enough, I have done I have done ghost imaging with orbital angular momentum. And what that gives you is it gives you omnidirectional edge enhancement of phase objects, but actually just in the same way you would do in the classical microscope. I mean, still the Klitschko model is a good simulator of the quantum effect. But if I put in to the system, I won't try and find the slide, but essentially what you do is you have You have the system here, and what you do is you add a spiral faceplate into this point, or actually in the Fourier plane, you put a spiral faceplate in here, and then when you look at the coincidence count, you get an enhancement of the edges compared to the DC. Yeah, and it's because you've got this sort of donut point spread function. But it's exactly what you'd expect classically as well. But thankfully, it also works in the quantum. I thought I was going to give a talk there without mentioning orbital angular momentum. Clearly, I failed. But
maybe last question? Okay, so I think it's not. So thank you.